Well, we consider a question coming from a paper that was taken by two groups, that is the Certified Public Accountants Foundation level and Certified Investment Finance Analysts Foundation level. The paper is quantitative analysis and it was taken in August of 2023 on the 23rd day. Now, the question that we want to look at is question 6, as you see projected on your screen. And the question reads, distinguish between a two-tailed test and a one-tailed test as used in inferential statistics. 4 marks. Part B, the data below shows the sales made by COSA Limited over a period of 6 years. Year 1, okay, we have years 2017, 2018, 2019, 2020, 2021, 2022, and the corresponding sales as shown. We are required to get the sales forecast for the year 2023 using exponential smoothing, and the smoothing constant is 0.2. Roman 2, the sales forecast for the year 2023 using the ordinary least squares method, or otherwise what we may we call generally as the regression method. Third, using suitable computations, advise COSA Limited on the preferred forecast method. So that being the question, let's see what our solution should be. Well, we consider a question from quantitative analysis. This is an examination by KNEC and taken by two groups, that is CPA, Certified Public Accountants, and Certified Investment Financial Analysts. So the question, as you have seen, is that, so I'll see what part A is. We are asked to distinguish between a two-tailed test and a one-tailed test as used in inferential statistics. So part A. Normally in testing hypothesis, we have what we call the researcher's hypothesis, which is the null hypothesis, and then we have the alternative hypothesis. They are denoted as such, as follows. Null hypothesis normally is denoted by H0, null hypothesis. And we have alternative hypothesis to mean if, because the researcher puts forth a hypothesis before setting out to carry out a research, and then collects data to ascertain the claim, actually to validate the claim. In validation, it is possible that the researcher finds that his claim is consistent with the data or not. Now, in the event that his claim is consistent with the data, he goes with the H1, in which case the researcher's hypothesis is true. But it's possible that data says otherwise. So when data says otherwise, then you have alternative. But now look at this situation. What if a specific example here was that the researcher is saying that the mean height of male adults in a particular city is, say they are saying it's sorry, they're saying it is 6 feet. I think 6 is much. Let's say 5 feet. Yeah, that's what the researchers say, 5 feet. But then he goes ahead to collect data to validate that claim. There are two chances here. One, that the data supports that indeed that is the average height of male adults in that particular city. Or the data may say no. Now, when the data says no, then there are two possibilities. It's either the mean is less than 5 or more than 5. Now, the fact that it gives us two possibilities which come as a result of this Those two possibilities come as a result of this. If you consider a standard normal table, we'll be having this tail and this tail. Now, the moment we are saying this is not equal to, it may be falling in this tail or in that tail, which makes it two test. Which makes it two-tailed. Two-tailed to mean if this is not equal to this, it could be higher than that, in which case it will be here, or it could be less. That makes it two-tailed. But what if we were talking about a variable that cannot be less than this? So if I say it is not this, then it would be understood that then it is greater than that, in which case it will just be here. That's one-tailed. And if it can only be less, then it's the other end. So that makes the difference between a one-tailed test and a two-tailed test in testing hypothesis. Now, the data below shows the sales made by Kuza Limited over a period of 6 years. So, I have data here. You take a sip of water real fast. Yes, I'm back now. Sorry for that. Okay, so I have here and sales. I have here in sales. Sales is saying M. So this is what we have. So we are saying that it starts from 2017, then 2018, 2019, 2020, 2021, 2022. 2022. So the corresponding sales are 80, 78, 72, 68, 70, 82, like that. So that's the data we are given. That in 2017 the sales were 80, the volume was 80. In 2018, 78. This up to there. So required the sales forecast for the year 2023. So here 2023. So we need the sales forecast for the year 2023 using exponential smoothing constant of 0.2. So part B solution. So I would say the exponential constant is that. And if the exponential constant is that, we should remember that the formula for getting the forecast at time t plus 1 will be given by this exponential smoothing constant, which is that, times the actual at time t. Actual at time t. At time t plus 1 minus alpha of forecast for time t. Forecast for time t. So what we're saying is that, for instance, to get forecast for 2023, that is F 2023, then it will be 0.2 of the actual for 2022 plus 0.8 forecast for 2022. Forecast for 2022. For 2022. Yes, that's what we will have. So it then means that before we get this forecast, we should already have a column here for forecasts so that we get it up to here. By the time we have a forecast that responds to 2022, then we can use it with this, because this is now actual. So this is the actual. See, these are actuals. These are actual sales. Actual sales. So forecast, you want to see if we forecast. Yes, now forecast sales. Forecast sales will be. Forecast sales will now have we now call them F, and they're in millions, but now let's see what they are. So what is the forecast for 2017? We say the forecast for 2017, because that's where we are starting, is just 80. That's what we have. So the forecast for 2017 is 80. That's the base year where we are beginning from. Then how do we get the forecast for 2018? Forecast for 2018 will be 0.2 times actual for 2018, which is 78, plus 0.8 times 80. 0.8 times 80. If you work this out, it should give you 79.6. You should confirm that using your calculator. It should give you 79.6. Then I want forecast for 2019. Forecast for 2019 will be 0.2 times actual for 2019, which is 72, plus 0.8 times forecast of the year before, which is 79.6. If you work that out, you should get 78.16. Now, try just continue with the same method until you get to F of 2022. Forecast for 2022 will be 0.2 times actual for that year, which is 82, plus 0.8 times what we'll find up above here. So let me just fill them, but I know you'll work them out and confirm. 78.16, 75.53, 74.42. Then, yeah, so that's what we want. So for 2021, so it will be 0.8 times 74.42 times 74.42. That, if you do that, should give you forecast for 2022 is 75.94. That's what we have here. 75.94. Forecast for 2022. Forecast for 2022 is 75.94. So now we want forecast. We now want forecast for 2023, which will be forecast for 2023 will now be 0.2 times actual. Actual for 2023 will now be actual for 2023. Actual for 2023. Now it's actually forecast for 2023 is equals to actual for 2022, which is 82 plus 0.8 times forecast for 2022, which is 75.94. So if you work that out again, you should get 77.15. 77.15 million. So that is the answer. That becomes the forecast for the year 2023. So let's see how the ordinary least squares method look like. That is Roman 2, because we are told that we get the sales forecast for the year 2023 using the ordinary least squares method. 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 We should know that here we are using what we refer to as the concept of regression. We can have regression and correlation. It's normally treated as a topic. But in this case, we want to see what regression looks like. So normally, just like we have equations of a straight line, but here we consider it a little different. Instead of saying y is equal to mx plus c, here we say y is equal to a plus bx. In any case, if you rearrange it, it still has the same meaning because it's a relationship, it's a direct relationship, a relationship of two variables which fall on a straight line. So then y is equal to that. But then it should be remembered, so where y is sales and x is time. So y is sales and x is time. X is time. So what we will have is that we need to estimate these coefficients. There is a and b. Now a here means that is the value of y when x is 0. That's what it is. So it's synonymous with the y-intercept. So b is given by the expression, that is this b, is given by the expression n summation of xy minus summation of x times summation of y all over n summation of x squared minus summation of x squared as such. Then a is given by summation of y minus b summation of x all over n. That's how we need to get, yeah. So if we are able to estimate these coefficients, these constants, if we can estimate these constants with where this is the slope parameter and this is the intercept, if we are able to estimate these two, then we can completely specify our equation. But then, how do we get summation of xy? How do we get, say, x squared? So, this is how it goes. And here, I'm just going to show, but then I leave you with the other work so that you input into the calculator and find out if the values you're getting are consistent with what we are suggesting. So in this case, y, we will redefine y. Let me just have it here. So I have y, have x. Now, y is years. So having this, I just noticed that I went off by the time I was here. But what I then need to explain what should have happened. I said that we should remember that y is equal to a plus bx is the line. Actually, it's a relation. It's the linear relationship that relates y and x, dependent and independent variable. So once we have y is equal to this, then as I said, then b will be defined by all that. and A will be defined by all this. But then, what I said is that we need to know what then X is and Y is. So I will just change something here. So where there is 2017, for the case of using a smoothing constant, exponential smoothing constant, here I put 1. So you start with 1 because that is the base here. That is the base here. So I'll be having 1, 2, 3, 4, 5, 6. And this is X because X is the time and time is on the Y-axis. Time we find it on the Y-axis because it's an independent variable. It's an independent variable. Then this is Y. Actual sales here become Y. Actual sales. So if that is the case, then I want to show you what those other ones should be. XY should now be this by this, which is 80, this by this, like that, up to here. 6 times 8, you write it here. If you add all the values that you get, this by this right here, this by this right here, throughout, if you add all this, that gives you summation of X here. That's what you put here. Now, for the summation of X, you just add all this. Just add all this, that gives you summation of X, and you put it here. Summation of Y is this. Add this. There are some, you put summation of Y. Summation of X squared. Summation of X squared. X squared. 1 squared, which is 1, 4, 9, 16, 25, 36. Add them. That gives you summation of X squared. That's what you put here. Then summation of X is just this. Add this and square. By the time you add this, you get around 21, then square that 21. That's what is here. Then substitute their values as such. If you do, you'll be getting 0.857 as the value of B. N is 6 because there are 1, 2, 3, 4, 5, 6. If you substitute the values, summation of Y, put here, minus this, summation of X over this, you get 72. So it means that our line is Y is equal to 72 plus 0.857X. And so the forecast for 2023 will be 72 plus 0.857. But our X now is 2023 will be occurring if this 2017, 2018, 2019, 2020, 2021, 2022, 2023. So 1, 2, 3, 4, 5, 6, 7. It's the 7th item. So that's why we put 7 here. Substitute, you get 77.99 million, which is approximately 78 million. And what we obtained using exponential smoothing constant, we got it to be about around 77.15 million. Then the last part is asking us that with computation, we should settle or advise CUSA on the right method to use. And we are saying that the right method to use here, because both of these methods give us solutions which are close together. But then, choice of the method should now depend on the nature of the data. If data is one that the forecasted sales should depend more on the most recent sales, then exponential approach, smoothing constant approach is the best way to go. But in the event that we want to see the long-term trend in the data, where it is assumed that it changes using a pattern, a definite pattern, which is this, then we would go for the regression. We would go for the regression or ordinary least squares method. But then we see that if you look at the actual sales, we see that from here things just changed. Yeah, things just changed. Now that kind of response would mean that we may not rely so much on the long-term prediction, because that's kind of a cyclical pattern. It then means that that particular change we can better capture it if we use the exponential smoothing constant, because that will concentrate on the most recent data. So that is how you are supposed to answer this question. If you followed that procedure and gave your answers as such, then you should have been in a position to score full marks. So if this interested you, then I ask you to follow me to my next video.